So welcome to the 2015 NASA Ames Summer Series. Space biology is important for many reasons. It informs our human exploration missions, it informs astrobiology, it informs our life support in space, and it informs how we function here on Earth. Most importantly, space biology is a science that looks at the mechanisms of biology or life. Space biology is also an integral part of NASA Ames research. We would not be able to do the science that we want to do or advance it without astronauts doing the research in space. But astronauts are more than just the people who do the experiments in space. They have a life that we could learn and inspire to do and follow. Today's talk, entitled Rats, Folks, and Jellyfish, Studying Life in Space, will be given by Astronaut Dr. Rhea Seddon. Rhea began her career by receiving a degree, a Bachelor's of Arts in Physiology from UC Berkeley in 1970. She followed that with a medical degree, an MD degree, from the University of Tennessee College of Medicine in 1973. After completing her degrees, she went and followed and did both an internship and a residency in surgery, completing the residency in 1978, whereupon she joined NASA as an astronaut. She was one of the first 6 women to enter the astronaut program. She's a veteran of 3 shuttle missions: STS-51D on Discovery in 1985, STS-40, which also stands for SLS-1, Space Life Sciences-1, where she was a mission specialist in 1991 on Columbia, and then STS-58, SLS-2, payload commander this time on Columbia. That's quite an achievement, both being a doctor and astronaut. But she didn't stop there. So in 2010, she got a certificate in creative writing from the Middle Tennessee State University. So you would think that after all of that, you would just retire from going to school. She finished that and then put that into action and wrote a book and published it. So with that, please join me in welcoming Astronaut Dr. Rhea Seddon.
Nicely done. Thank you, Dr. Cohen. As you can tell, it's been an amazing life. And people say, how in the world did you go from this to that to this to that? And, you know, for me, it's interesting to ponder that. When you get to be my age and you begin to think about, well, what happened that made me do those things? I can remember being a small girl in the backyard of a small town in Tennessee, and my father said, "See?" And there was Sputnik. So even at 11 years old, I knew that that was the beginning of something awesome for my generation. It was the beginning of the space age. And of course, there didn't seem to be any place for me in that. They weren't even flying humans yet. And even when they began to fly humans, it was only men, it was only pilots, only test pilots. But I was interested in science and was fascinated by the human body. And so when I finished high school, I thought, well, what is the best university in the United States in the life sciences? And it was this strange place called Berkeley. Now, I'd never been to California, but I applied and was accepted in 1965. And for those of you who are old enough to remember, that was an interesting year. That was the free speech movement. And that morphed into the anti-war movement and the People's Park movement and free love and drugs. And there I was in the middle of it. I sort of felt like later on when I watched the movie Forrest Gump, it's kind of like, here I am, and why am I here? But I certainly got a good education at Berkeley, both in physiology and in life in general. But I was one of the few people at the time that was majoring in science. Women just didn't do that, particularly women that I knew. Luckily, I had some good mentors along the way. But as I was finishing Berkeley, I thought I'd really like to go to medical school. But you can imagine coming from Tennessee, my first couple of years at Berkeley, I struggled to keep up with all of the rest of the people who were pre-med. About a third of the class started as pre-med students, so there was a lot of competition. My grades weren't great. I joined the pre-med club, and the advisor kept saying, if you don't bring your grades up, you'll never be able to get into school. And of course, getting into the California schools was close to impossible unless you had a 3.98. When I applied to medical school, I had a 3.25. My last 2 quarters were straight A's, and apparently that counted for something. And it certainly counted for something at the University of Tennessee, where not too many students were applying from Berkeley, as you can imagine, but Berkeley had such a great reputation. But they were not taking very many women in medical school back then. It's hard for young women today to realize that women were just not being taken into those fields. But the University of Tennessee, the year I applied, decided that they were going to take a lot of women because there was a big push to train more women doctors. So in a class of 100, they took 6 women. That was a lot. It took hard work, it took dedication, and it took fitting in with a group of men and learning to work with men and with male professors. There were very few female professors. There were a lot of nurses that helped along the way, nurses who hoped that women would succeed in medicine. So I was fortunate that was part of my background, learning to work with all kinds of people. My skills, my talents, my interests fell into the world of surgery. And if it was strange to have a woman doctor, it was even stranger to have a woman surgeon. But I applied to the university program and was accepted and was the only woman that they'd ever had in the surgery program. But again, lots of hard work, lots of people who wanted me to succeed, and I was successful in that. And so I was going to go be a rich surgeon. That was my future. I loved it, and so that's what I was going to do. One of the professors that I worked with said, "You should come out to my flying school. I have a flight school out here. You'd love to learn how to fly." And I thought, I'm going to be like him and have an airplane when I'm a rich doctor. So I asked my father for flying lessons, and he gave me flying lessons, and I got my private pilot's license. And then all of a sudden, rather serendipitously, if you read my book, you'll see how strange this was. I found out that there was going to be a selection for Space Shuttle astronauts. Well, people kind of didn't even know in 1977 what the Space Shuttle was going to be. But I wrote for an application just to see whether or not I met all the criteria to apply. And I did. You had to be at least 5 feet tall, and I made that by 2 inches. And you had to be in good health. You had to have a bachelor's degree, preferably an advanced degree, and preferably experience in your field. And they took my residency, my 4 years of residency, as experience. I thought it was more school, but they thought it was experience. So I applied to the space program. Lo and behold, in the summer of 1977, I was called to Houston for an interview. And they were going to interview 220 people and in groups of 20. And I asked when they called, well, how many actual people applied? If you counted all the military applications, there were 10,000 people. So I felt like, man, if nothing more happens, I made the cut down to 220. Went down to Houston for a week. And it was the first group of mission specialists or non-pilots that were being interviewed. And so Monday morning was when we went on Sunday. We're going to have a week of interviews and physical exams. My interview was scheduled for 10:30 on Monday morning. In looking back at the records, I was the first woman that they ever interviewed for the astronaut program. The first two groups had been all male pilots. So that was an honor in itself. I made it through the physical exams, the psychological and psychiatric exams, the claustrophobia exam, many, many different things, and sort of went home with lots of souvenirs because I figured I'm going to have souvenirs of this. Well, you know, in January of 1978, the call came and said, "Are you still interested in this job?" And of course I was. It was like coming to Berkeley. I wasn't really sure what I was getting into, but it sounded like the most fascinating thing that a person could do at the time. And so I joined the Astronaut Corps and started work with NASA in July of 1978. So I'm going to tell you a little bit about that. In that class, they took 35 astronauts, and 6 of us were women. The women who had been interviewed all thought that they would take 1 or 2 women, but not 6. So we were delighted that there were the 6 of us. We were very different. We came from different parts of the country. We had different backgrounds, all in science, astrophysics, geology, engineering, biochemistry, medicine. But we formed a bond, as you can imagine. We were afraid they were going to wash us out, that they would put barriers in our way that would see that we didn't get to succeed. But we were willing to support each other and to go through this together, and it turned out that we all had a chance to fly. So it was a great group to be a part of. You can see I'm the runt of the litter. And in fact, it wasn't as hard being female. It was really hard being little, because there were a lot of things that NASA hadn't thought of, couldn't accommodate a 5'2" female. The height requirement, I think, for the men was 5'6", and so there was a lot of equipment that they forgot didn't fit a 5'2", but again, you worked that out. For the first few years I was at NASA, the shuttle wasn't flying. Remember, I was accepted in 1978. The shuttle didn't fly until 1981. But I was anxious, besides all of the training that I was going through, to get involved in some of the life sciences and the medical operations experiments and tests that were being done. And so I jumped at the chance of flying on the 0G plane. This is a large commercial airliner that's been cleaned out. The inside is cleaned out, so it's an open space. It flies up and down like a roller coaster. At the top of each parabola, you get 30 seconds of weightlessness. And so if you can take all of the things, the processes and the experiments that you want to do, break them down into 30-second segments, you can practice being in 0G. And that was as close as we could get while we were still here on Earth. So here we are trying to develop a way to do CPR in weightlessness. For those of you who've taken CPR, you know that one of the things you have to do to pump the heart is you have to put your weight on that chest to push the heart. How do you do that in weightlessness? And so we were working that out. It was lots of fun. It gave me the best experience I could get at the time of being weightless. Luckily, I did pretty good jobs and was assigned to cruise. This is STS-51D. I'm proud to say the commander of that flight, Colonel Bobko, is here today to watch, and he's going to keep me straight if I say the wrong thing. And come up afterwards and say, your commander says you got that wrong. So Bo, I hope you enjoy the talk. Here we are. We actually ended up training we had 4 different crews and trained for 4 different flights, had 4 different patches because our flights kept being canceled or postponed. But we eventually were able to get off the ground in April of 1985. Strange to think it was 30 years ago, Bo. We haven't gotten a day older, have we? We had a great time. It was primarily a flight to launch a couple of satellites and do some orbiter testing, but they did put some science on board for the scientists that we had. Here I am. This is weightlessness. It's a joy, but it takes some getting used to, and that's really what I'm going to talk to you about today. I'm not going to tell you all of the data results from all our tests, our research and our experiments. I'm going to tell you about the challenges of doing life sciences research in space. And that's one of the things that astronauts really were therefore was helping scientists translate what they had done in the lab into something that could be done in flight. This is the American Flight Echo cardiograph machine, the first time that we were able to look inside the human body at the heart using ultrasound to look at what happens to the heart and blood vessels when you go into weightlessness. This is the middeck of the shuttle, and there were a number of small middeck experiments that NASA put on board, mostly to look at operational issues. Operational meaning things like your heart, your blood flow. And so this was an experiment that was put on board for me and that I had trained on a lot on the ground and thought I knew what I was doing until I set up the equipment. And you can see the problem here. Everything goes haywire. It won't lay down like it does here on the ground. You've got all the wires, you've got your equipment floating away, your checklist has to be taped to the wall, you have to get it all set up, and you have to get used to the fact that that's going to happen. So this was great experience for me on my first flight. Here we are doing that experiment, and it almost looks like we're standing on the ground, but we have our feet in foot loops on the floor to stabilize ourselves. Here I am with Jeff Hoffman looking at his heart. You can tell how tall and thin he is. His heart's right there for me to look at. But lo and behold, his heart swung out a little bit. It was in a different place in weightlessness, and so I had to fish around for it. But you can see we're a little bit better organized. And the way you can tell that this picture was taken in space and not on the ground is the bumper stickers in the back. We like to advertise our schools. Jeff went to Amherst, I went to the University of Tennessee, and we tried, when we were taking nice pictures, to bring back home to slap those on the wall. We obviously didn't do that in training. They do let you take a few things with you when you go into space, just so it looks like you're really in flight. Lots of good information came back on 4 subjects during this flight. We even trained one of our payload specialists to do some studies on motion sickness. This is Senator Jake Garn. He's the first politician in space. He was a senator from the state of Utah. A lot of controversy about flying politicians. But Jake got a lot of experience here. You can tell that he was very suited to doing the brainwave test by his hairline. That's why we told him that that was the one he needed to do. But looking at space motion sickness, the press sort of had a heyday with making jokes about poor Jake doing motion sickness studies, getting sick in space. He's a pilot, he'd never been sick. But anyway, Gary Trudeau did a series in Doonesbury calling him Barfing Jake Garn. And he did really well in space at barfing. He certainly did a lot of work for us, and later on in some of NASA's dark days, it was very helpful to have him representing us in the Congress, and he was very well respected because he had been there and done that. So here's Jake, but you can see he's got to put all of his equipment in a place, stabilize himself in order to get the good science. So it can be done by private citizens, but it works a little bit better when you do it with people who know the science. I was fortunate. About that time, I was assigned to another space shuttle mission. It was called Spacelab Life Sciences-1. The Life Sciences Space Labs were not operational issues, they were research missions. And NASA sent out announcements of opportunity to scientists all over the world to propose science. Lots of proposals came in, a few were selected for flight. Certainly, I think even some of our experimenters and our research scientists are here today to hear the talk. Very complex mission, an integrated mission. The Spacelab missions that had flown before had a little of this science, a little of that science. This was the first time a mission had been dedicated entirely to life sciences. And so we could test many different systems and see what was going on inside the human body. It doesn't help to look at your heart if you don't know what your kidneys are doing, what your blood pressure regulation systems are doing, what's going on with your metabolism. So it was a wonderful mission. It was the mission that I came to NASA to fly. We had our crew picture done. We were 3 physicians there in the front row, and Millie's a biochemist. She's from out this way, an invaluable member of our crew, and we're getting ready for our flight. We're wearing the big orange suits that were worn after the Challenger. This was in 1991. and we're all looking very formal in our attire, in our formal picture. But crews, of course, like to have a little fun. And in the NASA archives, you will probably never see this next picture, but I'll show it to you. Here we are, goofing off. We decided we were the perfect MASH unit. You can see Hawkeye and Trapper John. You can see Father Mulcahy, Hot Lips. And being named Ray, I had to be Radar, of course. And none of the men, for some reason, wanted to be Klinger, the cross-dresser. And so Drew Gaffney drew the short straw, and he got to wear the dress. So we did have a little bit of fun with it, but it was a great crew. I'm going to show you for the second Life Sciences mission. I had gained a lot of experience on the first one. I volunteered to make the second one because I thought we could make it more efficient. And we had learned a lot about doing all of these science experiments all clumped together, how to coordinate everything and make sure the data was good. And so I volunteered for this mission. It was the first time that I had worked with Ames, I think. They were in charge of the non-human experiments. The animals, the jellyfish, the things that we flew that were not people, they were managed here, and I got to know an awful lot of just great people out here. So anxious to be a part of this grand endeavor, and worked so hard to make sure that everything that we wanted to do got done. Again, a great crew. We had 3 payload specialist candidates that trained with us. One flew, Dr. Marty Fettman, the first veterinarian in space, because we were going to carry animals on the mission, and it was helpful to have him there to represent the animals. And Dr. Larry Young and Dr. Jay Bucky trained with us, didn't make the flight, but they were representing us in the Payload Control Center on the ground. An invaluable resource. They had trained, they knew all the things we were going to do, and really represented the crew in the Payload Control Center. And of course, we had to have an informal picture, and we thought, okay, what are we? We are going to stay in space for longer than any other mission had stayed. And we had so much crammed on board that we had to stow, we had to train on, we had to know where it was. I mean, what did this feel like? Well, it sort of felt like a family camping trip. So here are the happy campers. I hadn't realized till I looked at this picture how many hairy chests there were on this flight, but here we are having a good time with some of our science and some of our camping gear. But again, crews always enjoy having a little fun, and you train for so long under such amount of stress that it's good to have a chance to laugh every once in a while, mostly at yourself. This is Spacelab. Spacelab was a working laboratory that sat in the cargo bay, at the back of the cargo bay, about 15 feet in diameter, 23 feet long, and a working laboratory where you could put all your lab stuff. The mid-deck of the shuttle, very cramped, and it's living quarters, so it was very helpful to have lots and lots of room. And when you're on the ground and you're looking at this and everything is neat and put away, you think, we've got lots of room to do this. Well, it fills up fast. And it fills up in many dimensions. Imagine if we in this room could use all the real estate that's up above us. We're using maybe a third of the space in here. There's a lot more real estate. And that's what we had to learn to do when we were in the space lab. You see Millie up here? We had lots of stowage. We learned how to hook our feet on the handrails and open up this, and it was a great place to stow. On the ground, it was kind of a pain to get stuff out of there, but in space, it worked well. Lots of checklists, lots of things out that we needed to leave out because we were going to do something later that day. Lots of people back in there. Who's that? Anybody know? Looks terrible. Not space motion sickness. That's Recessa Annie. We did some tests of doing CPR. Remember the one that I did early on? We took Recessa Annie with us to do a little bit more formal studies there. But again, learning to do it in a very different environment. The scientists know how to do it in their lab. They have no idea how they're going to do it up there, and that's the role of the astronauts. And that was part of the fun that we had, trying to think about how are we going to do this, and what's it going to look like, and what do we do if it doesn't act that way when we get there, and figuring it out to get the job done. Many, many experiments, a lot of people counting on us. the scientists said, you are our eyes and our hands in space, and we took that responsibility very seriously. Just to show you, this is one blood draw. We did metabolic experiments, and we had 4 subjects, and we were going to have to get up in the morning before we ate breakfast and draw blood samples. We'd injected tracers, and this is it all set out. We had trained, we had planned, and we worked out that this was the most efficient way to put the most stuff in one small container. And here it is. This is 4 subjects. You can see we all had different colors. You may not be able to see it, but the colors here, the red, orange, green, and purple, I think, each crew member had a different color. So our tubes were color-coded, everything was color-coded with our specific color, so that when it came back, we knew that that was Ray's blood or Millie's blood or somebody else's blood. So this was all laid out for us. And you know, it looks complex. It was even complex when you had to use this stuff. This is a blood draw using that tray, and look what's going on here. Millie's the subject. She's having her blood drawn by Drew. She's holding the blood that has been drawn already. He draws the blood and hands it to her. Jim is pulling out the tubes next. He's looking at the colors, the time, which one of the blood draws is that, and hands it to Drew to draw the blood. Now, it's really helpful to have plenty of help when you're doing this. The other thing that's going on here that maybe is a little bit more subtle is they can cross-check each other. If Drew was trying to pull those things out, he might pull the wrong thing. But Jim pulls out the tubes, he looks at them, and then Drew, before he draws the blood, gets to look at them again. So that's called cross-checking. And it's really helpful, certainly in medicine, for instance, if you're going to get a pint of blood, that 2 people look at that and cross-check and make sure you're getting the right stuff. Or if somebody's going to operate on you, it's nice to have somebody there that's going to cross-check to make sure you're the right person and the right procedures being done. So cross-check is one of those things that's a very nice life skill and something that we learned how to do so that we didn't mess up when we got to space. I have to tell you a little story. As we're going out to the launch pad for this mission, the chief of the astronaut office has to get off the bus before we go out to the pad, and he said, I would like you to all bow your heads so I can say a prayer before I get off the bus. And we all thought, okay, very somberly. And his prayer was the astronaut's prayer. God help you if you screw up. So we remembered that. For the next few days, that was our mission to do that. And scientists, when they propose experiments, say, this is really going to be easy because I just want them to draw some blood and collect some urine. Now, if you're part of an experiment like that on the ground, that's not a big deal. You go in the bathroom, you collect urine. How do you collect urine in space? Many people don't know that, you know, there's a problem with that. As you can imagine, we use airflow to pull wastes away from the body. The air comes under the toilet seat and it pulls the urine into the toilet. We have a funnel that we can put that goes down the tube. How are you going to get a urine specimen? How are you going to measure the volume of urine that a subject puts out during the day? A special piece of equipment was designed called the urine monitoring system. Pulls the urine in, centrifugally separates the urine from the air. It can measure a volume, and it can pull a specimen out here. We all had our color-coded tubes that it was pulled into and put it in here. So a very simple thing to do on the ground, a very complex thing to do on orbit and to do it correctly. And so, again, science was easy for some of the scientists, and they couldn't understand why it was going to be so hard when they got into space. But there were things like that that had to be accommodated. How do you weigh yourself in space? Oh, you know, you tell the subject, go weigh yourself. This is how you weigh yourself in space. This is the body mass measuring device. You sit in this chair, strap in, release a spring, and the heavier you are, the slower the spring rocks back and forth. The computer can calculate your weight. So a simple thing done on the ground, a very complex thing done on orbit. And we had to learn how to do this to do it accurately. And operationally, you know, you practice things on the ground, and then you get into space, and you can't quite do them the same. This is looking at blood flow to the leg. There's a problem when astronauts stand up after they get home. Sometimes they get lightheaded. The idea was maybe the blood is not getting back to the heart as well. So this is an experiment. Usually in this, the subject's lying down when you do that. But look how much easier it is to do this here and do it this way. But sometimes you have to do it a time or two to say, hey, you know, it works better this way. I just put my subject up there and the operator will be down here next to all the equipment. Works much better. So operationally, sometimes you have to not only have different equipment, but have a different way of thinking about what's possible. This is an experiment that put pressure or suction on the blood pressure sensors in the neck to see whether or not the heart responded, whether that was one of the problems with dropping blood pressure when you got back, if those reflexes got out of shape. But as you can imagine, you have to worry about the safety of experiments like this. You know, I'm going to mess with your blood pressure receptors and it's going to do something to your heart, and you're going to have to monitor what do we do if you have a bad reaction to that. So there was a lot of planning for worst case scenarios. You know, what are we going to do? How will we recognize it? And then how do we deal with it when we're in space? Luckily, nothing happened. But again, the exercise of proving to our safety organization that it was safe to do this. This is how we did exercise in space, and tell you a little bit about that. We were wondering how much exercise could you do, what was your intake of oxygen, output of CO2, you know, what does that look like? So here I am on a bike, but it looks a little odd. What is this? There's a similar one on the other side. You can imagine if you're sitting on a bike bolted to the floor and you start pushing the pedals, you're going to go the opposite direction. So you have to have something to hold you down. Those are shoulder boards that hold you down to the bike so you could do the exercise. One thing that we had not thought of for this experiment, because you went to maximal exercise. So the guys are there and you know, they're big mooses. They're doing big time exercise and they start to sweat. If you ever sweat on the bike in the gym, it goes on the floor and you clean it up afterwards. Where does it go? It blobs up. And here you are, you float by, and there's this giant blob of sweat hanging off the back of this guy. So we had to have helpers to go around with a towel and keep the sweat in one place. Another thing that I'm often asked, especially by kids, you ever see any UFOs or aliens in space? And I said, no, I haven't. But quite frankly, occasionally we catch them and see them in pictures. What is this? That's an alien. That's a crew member. He just kind of looks weird in that picture, and people say, what is that? That's our alien. This is doing a lung function test. Dave Wolf is breathing on this machine to look at how your lungs function. Again, easy to do on the ground, uses a gas called argon. There are other things on their gases or liquids that turn to gas, like Freon in the freezers. One of the things you had to prove was that if all that gas leaked out, it would not reach a dangerous concentration in the space lab. And so that was one of the other things that we had to worry about. How little gas could you use? How to keep your subject safe. This is a subject doing a vestibular test, rotating in the chair, but you can see he's blindfolded, he's strapped in. If something happened, an emergency happened, he gets disoriented doing this. How do we get him out of there safely? So things that you frequently don't have to worry about on the ground, you have to think about when you get up there. Jellyfish. The title of the talk talked about jellyfish. Interesting that we took some flasks of jellyfish, we injected them with hormones. Jellyfish start like these little polyps. They get some thyroid hormone and they strobilate, they turn into little sections, and they float free. And they form statoliths that are kind of like the otoliths in your ear, little stones that tell them where up and down are and whether they're moving. The question is, did they develop them in space? And they did. That's obviously hardwired into their DNA. They swam in circles up there, but they could swim just nicely when they got back down. So a simple experiment. But it was fun to do and fun to watch the little jellies swimming in their little flasks. We took animals into space for the first time, lots of rats. They had flown in sealed containers before. This was the research animal holding facility, a massive project by the Ames folks. The first time the research animal holding facility flew, it didn't function very well. The airflow was not very good, and some of the air came out. And when your commander is sitting up in the cockpit, and he looks up and he says, "Oh shit." And that's what it is, because it's come out of the animal cages. The people back in mission control get a little freaky, and so the animal cages had to be redesigned. We didn't think we would have them for this mission, but because we were delayed by Challenger, they were redesigned in time. Thank you, all you wonderful Ames people that worked so hard on this. We flew them on SLS-1 as a test. We're pulling them out. We got permission to pull them out of the holding facility. The animals were healthy, the cages were working well. We pulled them out, took them over to a workbench to see how the animals reacted to weightlessness. They didn't get aggressive, they were easy to handle, and that was a good thing for SLS-2 because we did animal dissections for the first time. And you can imagine, if you remember your freshman or sophomore biology class and dissecting a frog or dissecting an animal, imagine planning to do that in weightlessness. A lot of stuff about the animals themselves, the tissues that we had to save, the fixatives we had to put them in, the instruments we had to use, the time constraints that we had, and we practiced and practiced and practiced and practiced thanks to the amazing people here at Ames that helped us plan that and do that, put all the stowage for us. And they breathed a sigh of relief when we voiced down. We did 6 animals and we got all the tissues that we meant to. So it was amazing. We wanted to compare the reaction of the rats in space to people to see whether or not they were good models for humans. So a very, very important part of what we were doing on this mission. When we come back to Earth, you know, you're above the atmosphere when you start out, and when you enter the Earth's atmosphere and you hit all the air molecules, it heats up the shuttle. You have to be protected from that heat. And this is what it looks like. And the folks at Ames Research Center were in charge of the thermal protection system. And we owe our lives to the people that designed this remarkable system of insulating blankets, reinforced carbon-carbon, and all the tiles that fit on the bottom of the shuttle. And this is what it looks like when you're in the midst of that fireball. And you realize how much your life depends on that system. I'll read a little book, a bit out of the book. After a successful deorbit burn, the orbiter flipped over so that its nose was forward again. The nose had to be cocked up about 40 degrees so the heat shield tiles on the underbelly would get most of the heating during re-entry. As we sank deeper and deeper into the atmosphere, an orange glow began to appear out the windows. Behind my head, heated air molecules struck the tail and created bright flashes of light on the backs of Brian and Sid's helmets. We were in a thin-skinned protective cocoon in the midst of a fireball as hot as the surface of the sun. If there were any breaks in our vehicle's skin, we'd soon be incinerated. So you really think about the people who are looking out for you and who have done remarkable things like this. And so again, thank you to the Ames folks. You always hope that you have as many landings as you do takeoffs, and I was fortunate that I did. This is my last landing. Instead of getting out and kicking the tires, we had to move into a people mover to get back to the lab because we had normal testing before we left. We were tested in flight, and then they wanted to see how we adapted to getting back to Earth. So it was wonderful. What great experiences I had, and how fortunate I was to be able to do all these rather unusual things. I wanted to capture those things. I put them down in a book. It's not a great work of literature, but it is a simple story of what it's like to go from being a little girl in Tennessee to getting to go to space and having kids along the way, marrying a fellow astronaut, getting to be an astronaut spouse, and doing great things. The logo on the left is the astronaut symbol, slightly modified, and it is the logo for my book. So again, I appreciate your being here, and we'll do some questions and answers if we have time.
Yes.
All right.
Thank you, Ray. If you have a question, please raise your hand, wait for a microphone to come to you and ask your question, and then return the microphone. Thank you.
Thank you, Dr. Seddon. On behalf of the astronauts and women and kids of all ages, you really are quite the inspiration. I didn't have a question, but I just wanted to congratulate you on your induction into the Astronaut Hall of Fame 2015.
Thank you so much, Yvonne. I appreciate that. It was quite an honor. You know, I heard a talk recently by an astronaut scholar who talked about the value of recognition. You know, when you think you're doing a pretty good job, you're not really sure until somebody rewards you in some way or mentions you in some way. So I always try to remember that, to tell people how much we appreciate the things that they've done for us. Other questions?
You talked a little bit about some things that are more complicated in space than they are on Earth. Is there any one thing that scientists usually fail to think about when they're thinking about space experiments, or something that you thought was interesting?
I guess, you know, one of the easiest things to do in space is to move around, because you fly everywhere. And so getting from place to place is relatively easy. So it's easy to do that. I guess one of the things that the scientists often forget on complicated missions like this is that you have 4 subjects, you have lots of experiments, and they have to share, they have to coordinate with other scientists. And frequently that's a bit of a leap for them. They're used to doing their science, and you have to work to put everything together. Certain experiments can't be done back to back. And that integration is sometimes difficult and requires a lot of coordinating and compromising, and so I think that's one of the things that made it a little difficult. As the payload commander on my 3rd flight, I got a chance to help with doing that, and I think we built a great team, and we all wanted to help each other out, and so making that work was one of the more complicated things. Scientists are used to doing their science in their lab and having all the time.
Hi, Dr. Seddon. Thank you for your talk today. A good number of us got to work with Bob Phillips in the years after SLS-1, and so he passed a couple of years ago. I'm wondering if you have a good memory that you might share with us of something, since he didn't ultimately get to fly, but I know he served as Capcom on the mission. But
Bob Phillips was a veterinarian who trained for us for SLS-1. Wonderful, wonderful guy, and we just loved him. He developed a health problem during our training that made him ineligible for flight. And we wanted to remember him in a way. We couldn't put his name on our crew patch, and that was unfortunate. We felt he should be remembered. He represented us in the Payload Operations Control Center. Do you see the P? P for Phillips. So we were happy to be able to do that, and I think it was special for him. And you know, he lived many, many years with that health problem, and probably wouldn't have affected his being in flight, but we were sorry he didn't get to go. But he was so excited about the mission itself. So thank you for mentioning Bob. Wonderful guy.
You have been such a trailblazer and accomplished so much in your life. What is your next goal?
I mentioned that I had married a fellow astronaut, Captain Hoot Gibson, a pilot astronaut. He commanded 4 shuttle missions. He flew as the co-pilot on his first one. I would love to write his book. It is a totally different book. It's the pilot side of things. But just as I served as his spouse during his missions, he served as my spouse during my missions, and has many funny stories about it. Bo can tell you that he's quite a character. One of his flights was known as swine flight. If you read the book, they all snorted at pretty girls, and of course that wasn't politically correct, but they did it anyway, and so they were known in the office as swine flight. But he made it fun. And as I mentioned, if you can have a crew get together and have fun in the midst of all this stress, it's wonderful. So I think that's my next one. I'm hoping that he'll let me do it. I learned a lot by doing this first one. We have a question down here, if you got one back there.
Hi, thank you very much for the talk. In the cramped conditions of the middeck and the space lab, how did you avoid, or what were the countermeasures in place to not like bump into a switch or snag on a wire or something like that? And
Right.
did you ever mess up an experiment because of something like that?
I'd like to think we didn't, and probably someone has. The important switches are guarded. There are little things around each switch, and the ones that are critical, the ones up on the flight deck above the captain, the commander in the pilot seat, all have guards down over them. So in order to activate them, you have to lift the guard to move the switch. Occasionally things got kicked or bumped. Everything was made very sturdy. The plugs that we plugged in were super heavy duty and had to be screwed and locked in. But it was one of those things that you had to worry about. You couldn't just go flying around. And you learned how to move smoothly and gently and watch things. I think there was probably, we went back in the lab to play around one day and took some pictures, of off hours with astronauts, and we're goofing around. And when we were done, there was an experiment that had been turned off, and we probably kicked something in that area. We'll never know. But I can't think of any major catastrophes, things that were broken or not. Everything had to be super strong to deal, to keep the safety people happy. Not a lot of glass to break or things that were too delicate. So we had to worry about it. One down here.
Did a lot of experiments related to weightlessness. Did you do any experiments related to space radiation?
Space radiation, it's kind of one of those things that we worry about for going into interplanetary space to Mars, and I don't think we have all the answers to that. We did wear radiation monitors, so we made sure that at least when we got back, they could tell us that we hadn't had a lot of radiation. It was interesting on SLS-1, when we got back and we were saying hello to everybody, somebody said, "Could you feel that sunburst, those sun things, whatever it was that was, that had a solar flare? Could you feel the solar flare?" And we're going, "What solar flare?" And I guess the folks in Mission Control decided that it wasn't going to be a problem. They didn't even tell us about it. And I don't think the radiation that we had was that much higher. I know that we go back to NASA every year for physical exams. And they watch astronauts to see if there are any untoward effects that they can say were caused by radiation. But no, I didn't do any of the radiation experiments. I liked life sciences instead. How are we doing?
Good.
Hi, thank you for the talk today. My question is, what was going through your mind on your very first mission right after the solid rocket boosters ignited and liftoff occurred and you realized that you were going to space?
My first thought was we blew up. You're sitting on the launch pad and you're looking at the sky, and of course you're very worried about whether you're really going to get to go or not. And Bo can tell you that until the very last of our launch window, they said, hey, Commander, what's the best way to get this thing off the ground? And Bo said, "I think you could pick up the count." And he said, "Okay, in 30 seconds, T-minus 9 minutes and counting." So it was, it was just kind of like, oh, we really are going today. We had decided we weren't going. And you're sitting there and when the main engines start, the top of the shuttle rocks back, and so you can see the launch tower, and you can see that you're rocking back, and when you come to upright, the boosters are going to ignite. And there's no way for anybody to tell you what that's going to be like. There's no simulator that simulates that. It really, really feels like an explosion. And I was looking at my hands in my lap and thought, I'm going to watch my body disintegrate. And luckily I was on the flight deck and I could look at the computer screens and see that we were still going in the right direction. But the ride on the boosters is just incredible. Lots of noise, vibration, acceleration. And that first launch, I think there's nothing that can prepare you for that, other than somebody telling you it's going to be something like you've never felt before. My husband describes it like it's a catapult off a carrier, just an all of a sudden jerk. But yeah, you have to be willing to take that risk and be ready to go. In the back.
Hi. So my question is, when you were talking about when you were a young girl, you had a lot of people believing you and propelling you forward, mentors and things like that. So I'm wondering, what was it that made them believe in you and want to do that? And like, what advice would you have for young women who are, have these sorts of dreams and want to be pioneers today?
Well, back then there were just certain things that women were supposed to do, certainly in the South. But luckily my parents had some friends, a couple of women doctors, and they told me, you can do it if you want to do it. I had a father who was very supportive. Of course you can do that. There were a lot of dads that said, ladies don't do that, girls don't do that. And so I had a lot of support at home. But they were just things that I wanted to do, and I was going to try to do them. I always had a backup plan. If that wasn't going to work, I'd try something different. But as I went along, luckily, I met enough people who told me I could do it. A few people who, in subtle ways, told me I couldn't do it. But when you want to do something passionately and you want to try to do it, it doesn't hurt to try, and that's what I tell young women. Follow your dreams, reach for things that have never done before. Don't be afraid to go first, because if you really want to do it, you'll figure out a way, or figure out a way to do something similar. So, I encourage women who have achieved to please tell young women that they can do this, that they can do that they can do what you do, they can do what you wanted to do but couldn't at the time. I was fortunate I was in the right place at the right time. And so I think I was lucky in many ways. The good Lord looked out for me, I guess. Other questions?
Thank you for sharing your experiences with us. I think a lot of the vital information on the effects of weightlessness on humans has been researched for many years. Every single mission, and I think that a lot of the new things, while those macro scale experiments are still occurring and should still occur, a lot of the current experiments are more molecular. Where do you see physiological experiments going in the future? Where do you want to see us head in biological research?
I think that there are so many things that we could study. Molecular biology is certainly one of them. I think it's going to take NASA developing the equipment to allow us to do that, and putting crews big enough with enough training up there to be able to do that. Those of us who worked with the animals on SLS-1 and 2 were very disappointed when the animal holding cages and workstations were defunded for station. They're doing a little bit of it, but not with the sophisticated equipment that we were able to use on Spacelab. So I think there are many, many things that could be proposed and done. I think that there are animals that will be good models. We can use centrifuges. We can, put more sophisticated equipment for molecular biology up there. Many, many things that we can do. It just depends on the funding and the will to do it. I will mention that something that you said made me think about it. A lot of the science that had been done on humans had been done on men. And on these 2 flights we had men and women. And we compared the data, and men and women adapt to weightlessness just the same. So we'd answered that question. I'm sure there will be subtle differences that someone will be able to find out, but the major things were the same. Rats are good models for some systems and not others. Certainly cells would be wonderful to be able to take up cells and do studies on them without having to fly rats. But it's a brave new world out there, but we have the ideas. I think we have the technology. We just have to have the funding to make it happen.
As the commander on Ray's first flight, I had some concern that we had one woman and 6 guys on board. Well, with a strong professional woman like Ray, those were about the right odds.
Thank you both. Luckily, my first commander was a supporter and was always encouraging, and there were no major problems, were there? We had a good time, too. Always great to have a good commander.
So please join me in thanking Astronaut Dr. Rhea Seddon for an excellent talk. Thank you very much. Thank you.
Thanks so much.
Thank you.